Hello, everybody. Welcome to day 5, and hence the final day and final session of this ESO H0 2020 e-conference. For the duration of these announcements, please let's all turn on our video so we can say hello to each other. Just a quick reminder while we get started that using Slido, we can submit questions at any time during a talk. And to do that, please go to the conference program website and simply select the talk that you're interested in. And then you can click on Q&A and it will open a new window with Slido where you can then type in your question. The good thing about doing that early on is that other people will be able to vote for your question and give it a thumbs up. And therefore, the most relevant questions, or the ones that people are most interested in, will get relayed to the speaker by the session moderators. We also thank all the panelists and the speakers from the previous sessions for already answering the questions that were posed on Slido that did not get answered during the previous Q&A sessions and panels. And we thank Yes, we thank everyone for doing this. And we plan to post these replies on the program website as PDF files, copy-pasted from the Slack workspace. So they will be accessible to everyone. If those who sent replies on Slack disagree with us posting them on the website, please do let us know without delay, preferably on Slack using the hashtag #AskTheLock channel. We asked speakers and panelists to submit their talks via Slack, preferably in PDF format, so we can upload them to the website instead of publishing proceedings. They will be uploaded to zenodo.org, where they will receive a DOI and become fully citable. And we have been really active this week. Here are just a few impressions. Every day, we had between 220 and 320 live participants spread out over Zoom and YouTube. As of this morning, we had a total of more than 2,600 views of the conference videos on YouTube. So with this e-conference, I think it's safe to say that we've reached many more people than we would have in an in-person meeting. As of this morning, we had about 250 questions asked on Slido, 45% of which were anonymous. And I really couldn't help but notice that there's a strong correlation between how theory-heavy the talk is and how anonymous the people remain that ask the questions, me included. More than 1,500 messages we have exchanged on Slack, and this will stay open past this conference, although it's likely that this may fizzle out at some point, but nonetheless, the Slack workspace remains there for each of you to use. Please participate in our post-conference survey. Later yesterday, I sent out an email asking everyone to participate, and this is intended to make e-conferencing better in the future. For now, just because I have a little bit more time now than I have at the end of this session, I would like to say just a few scientific things that I've noticed and that we've noticed during this week, which is that, well, we sought, and I think we were successful in getting a very good bird's eye overview of some of the latest results on the Hubble discord, its implications, and also its connection with other cosmological tensions. I think it's really clear that there's very significant progress that was presented here and that's going on in this field, and there are very exciting advances on the horizon. There is very strong potential on several fronts to get to a 1% measurement eventually. And all this additional scrutiny from last year's KITP session, where frequently the plot from Licia Verde's paper that was reshared during this conference, we see that the discord still holds, and that really indicates that something genuinely interesting is going on. So this additional scrutiny, it's super important, and especially new systematic uncertainties being discussed and being dug out is really helping in making sure that we stand to benefit and learn from all this. There are lots of new ideas coming from theory, but I think as we heard yesterday, there doesn't yet seem to be a resolution. Nonetheless, lots of these theories that are being presented could be ruled out. And so it's really amazing to see theory in action like this. And of course, the tension in sigma 8 that has gotten stronger as the measurements have advanced really shows that there's a strong need to reconcile not only one, but several cosmological parameters. Some of the new topics that perhaps were not as prevalent in the KITP session, although speaking now from having read the article on it, is that peculiar velocities have become a subject that we've discussed a lot. And I think also the outstanding potential for growth in terms of the number of objects and also the precision gains for the, let's call them non-classical approaches, is really quite amazing. The standard sirens, for instance, or the strongly lensed quasars, and not least also, of course, the BAO measurements that are coming up from experiments like DESI or Taipan. So with this very short and arguably incomplete summary of what we've heard from this week, I would like to hand off to today's session, where we're going to have a look at what the future holds, and especially talk about future instrumentation like ELT, the James Webb Space Telescope, future probes of dark energy, and also the future of the cosmic microwave background. So for this, we have Giulia Fiorentino, Stefano Casertano, Elizabeth Krause, and Rafael Flauger among the speakers, and then among the panelists later on, Licia Verde, Tom Shanks, Saurabh Jha, and Jose Luis Bernal. And so for the first speaker, I would like to welcome Giuliana Fiorentino, who will talk to us about the ELT. So Giuliana, the floor is yours.
Thank you. Thank you, Richard. Okay, first of all, can you see my pointer, the mouse?
Yes.
Okay, good. Okay, first of all, I really agree with you, Richard, that the conference so far has been a really real success, and maybe he's going to give us the opportunity to meet more again with this e-conference. I was asked to talk a little bit concerning the distance ladder in the ELTs era. And here are some pictures about the three majestic telescopes that will be built, and we'll see their first light in the dates that I put in parentheses. They are the European extremely large telescope, the 30-meter telescope, and the Giant Magellan telescope. All of them have already started building their dome, and most of them already have a very concrete idea of the first light instruments, of their first light instruments. This means that these instruments already passed their preliminary design review, and so are approaching to the final design review. So after all, I think that we are really now today approaching to the ELTs era. I had the opportunity during the last 10 years to work a little bit on ELT, and in particular on its first light imager. This will be built on the Amazons, in front of Paranal site. And nowadays, a picture of the basement, it looks like this. So it's already going on. So as I said, I had the opportunity to work within the context of the ELT instrument for the ELT Coma, particularly with Mikado and Maori. These two instruments are more an instrument and a adaptive optics module. Mikado is the high resolution imager that will work as imager mainly, but also a spectrograph from I to K band, and will have the opportunity to use two different pixel size, 1.5 and 4 mass, milli arc seconds. So this means that this is an extreme high resolution imager. Of course, to make a giant telescope to reach their diffraction limit, you need adaptive optics that nowadays is a quite robust and consolidated technique. And you can have different flavors of adaptive optics. For the ELT Coma have been chosen two modes that are the single conjugate adaptive optics and the multi-conjugate adaptive optics. So both that are within the Maori module. I don't want to spend a lot on the different kind of techniques, but the most important thing is that they are They have a different kind of performance, of course. The single conjugate has a very high performance, but it needs a very bright natural guide stars to get very close to the target that you want to observe. Whereas the multi-conjugate adaptive optics mode has a moderate thread ratio, at least this is still in design phase, so still the properties are not completely frozen, and it will be fed by 3 natural guide stars with a quite faint magnitude, so H less than 19. The sky coverage for the multi-conjugate adaptive optics mode is much larger. Just to give you an impression of how adaptive optics works, so this is an example on 10-meter telescope of multi-conjugate adaptive optics here on top on the left, and single conjugate adaptive optics on the bottom right. In green, I highlighted the natural guide stars used for this observation. These are core of globular clusters, so very dense stellar fields. And you can see that the single conjugate adaptive optics in particular has a very variable PSF across the field of view. And you can see it by the elongation that has the PSF going from the center to the edge of the image. You can see here this ellipse. Okay, so to give you an idea of the kind of resolution and so the precision and accuracy that we will be able to reach with these giants, I show you an example of what we just published concerning one of the closest objects to our galaxy, the Large Magellanic Cloud, and in particular to a star-forming region, very famous, which is the star-forming region, and in particular for this cluster. This is R136. That today can be observed by using the best instrument ever that we have nowadays in our hands, that are HST, of course, and then a 10-meter telescope fed by adaptive optics, a single on the right and in the center multi-conjugate. You can see that the kind of performance that we obtain today are very good. In fact, you need to have in mind that in near infrared, an 8-meter telescope in near infrared has the same diffraction limit than HST telescope, so 2.4-meter telescope in V band. And this means that this is proving that adaptive optics is working very well nowadays, so it's a consolidated technique. If we try to make a simulation of what this kind of field would look like with the ELT high, we made this kind of experiment, and this is the result. So you can see that very faint stars will show up, and the resolution will allow us to distinguish among this blob that nowadays with the sphere are hiding a lot of stars blended and crowded around the very bright stars in the field. So this is the kind of resolution we will be able to reach. And what does it mean in terms of photometry? And so, for example, in terms of color magnitude diagrams. This is the color magnitude diagrams obtained with the data that I just showed you before. So real data on the right for HST and on the left for using the sphere at VLT. And this is what we do expect with simulation. So you can see that the kind of accuracy and the precision that we will be able to reach will be very, very high. And in particular also, this is true for astrometry that I'm not showing here, but will allow us to see signature in a very dense cluster of intermediate mass black hole at the distance of the Large Magellanic Cloud. So this is the scene. So how this scene can help us in setting the Cepheid distance ladder. This is the focus of my talk. And I divided the range of applicability of ELTs in 3, but I think that within our local group, in particular for our galaxy and the Large Magellanic Cloud, Gaia will be exceptional in improving the slope in the 0 point of the Cepheid diagnostic, so period luminosity, Vasenet, and etc. So what I think that the ELT will really can really help in helping the current distance scale would be the range of Cepheid supernovae 1A calibrators. So to be, what I have in mind is the full shoes sample, which I think we always need to give our credits because it's the kind of work that made possible the kind of conference we are doing today. I mean, it's a long-term project that allowed us as community to collect so many exquisite HST data that we can work at least forever for our careers. So on this data. And I will show you how we can improve and our interpretation of the shoe sample on the HST, of the HST data. And then we can try to reach Cepheid detection how to the Coma cluster, so where the Hubble flow is already can be estimated directly from Cepheid. So overcoming the calibration of supernovae 1A. Of course, this will have an error, but in any case, it is something that it can open a path. This will be possible thanks, as I said, to the resolution that we will be able to reach, that will be never reached from the space. So in some sense, I think that ELTs will become complementary to HST data or JWST data. In fact, a 39-meter telescope will have a very small diffraction limit that can allow us to reach regions that will be forbidden for HST and JWST. These here are just a few numbers to give you a quantitative idea of what we are talking about. If we take an ELT cam with the best 1.5 mass pixel resolution size, it will be in Coma sampling, it will be in Coma to sample 0.7 parsec, and in Virgo 0.1 parsec. So you can see the difference with JWST is a factor about of 7 with ELT, and with HST is even more, of course. Okay, so let's start with the first distance range. So where we have both Cepheid and supernova 1A that we can calibrate. So the full shoe sample galaxies, so if you want. I think that there we can try to investigate, to better investigate a problem that has been already discussed, in particular from Adam Rees during this conference, that is the crowding problem. The data, the HST data are excellent, but of course the distance of between 9 and 40 kiloparsec crowding is really making your data set very challenging. And also, I think that I'm not going to talk about that today, so not about spectroscopy, but with ELT and with different spectrograph on ELT, but also with the ELT cam, with the long slit spectrograph that will be in the first light instrument, we will be able to apply the J-band technique to resolved superstar clusters, and this means direct estimate of the metallicity of these galaxies, which is very important because usually these distances are not these metallicity are not stellar metallicities. So this will be very important. This kind of study are already possible today in antenna with CMOS. This is a nice work presented by Larden collaborators in 2015, and are suggested to be possible in the Maori White Book up to distance to Coma. So this will really improve our use of Cepheid diagnostic that do depend on metallicity. But let me show why we do need, I mean, we already saw some slide concerning the crowding. I want just to highlight once again that how we manage the data is very important, and also by doing the same kind of analysis, you can get a different result if you have a different data reduction, of course. This was a paper that I published in 2013 with other collaborators, and we used data from one of the first release of shoes. so RIS and collaborators 2011. So these are the 8 galaxies that they use for the estimate of H0. And we do compare in the color magnitude diagram this object with our theoretical instability strip taken for solar metallicity. And you see that if some of them are fully compatible with theoretical values, so there are some others that are really going to the blue. And this was suggested to be a problem of the crowding in the data set. The new data I have just put on top, the new data from recent collaborators 2016, so a revised photometry of the same set of data, and we see that this problem seems to be mitigated. So this is a good news. Also, we know that another observable, the amplitude ratio, is really important to understand the quality of your data, and is telling us the blend and maybe the direction of the blend. In this plot, I show you the optical amplitude ratio, so ADI on ADB, and this was with the old data, always from the SHUS team, so RIS and MACRI, for some external galaxy, and compared with the galactic Cephids. You see that galactic Cephid a very straight, narrow spread in all the range of period. For galactic Cephid that we know very well, we have very good curve for these Cephids. Whereas for the external galaxies, we do have a shift to lower amplitude ratio. And this has been also discussed by Riss in his recent paper and also in his talk in this conference. And I show you here on the left near infrared versus optical ratio of the amplitudes, and you can see here in the Large Magellanic Cloud, in the Small Magellanic Cloud, and in the Milky Way, how narrow is the spread around this amplitude ratio. We only have a shift for longer period. However, instead, if you look at the right panel, even though these are different epsilon y axis, you can see the ratio of the amplitude ratio between external galaxies and the Milky Way. And here you can see the things that I want you to notice is the largest spread that we have around this relation. So all these indications are telling us that crowding is important and we need to really quantify. This is why, because of course, if you use different data set, the same data set with different data reduction, you get different results. This was again from Fiorentino 2013. With the new data, I get this distance modulus using only a period luminosity relation in infrared, neglecting the problem that we could have in the color term V minus I. And the new Hubble constant that I get is 77.65, so 2% larger than the old one. I don't want to say that this is more tension, absolutely not. I'm just making a relative discussion to say that we need to improve and to be very confident in the data that we are using to make then a valid analysis and interpretation. Okay, to do so, we could use the astrophotometric performance of an ELT cam. I don't have ad hoc simulation for this case, but one of the scientific requirement for this kind of instrument was the photometry, the resolved stellar population in an elliptical galaxy in the Virgo cluster. So at the distance in the range of distance that we are talking about. This is what you see with JWST today, and this is what you hope or you think to see with the ELT tomorrow. So this is the kind of possibility we talk about. And to be more quantitative, I show you here an example between ELT and JWST. I want to make you clear that ELT is not going to go deeper than JWST. Although maybe it's going to be is not going to be deeper since there is the background that in near infrared that will at some point will make undetectable sources. However, they are complementary because ELT will serve a region of surface brightness, this is surface brightness and this is limiting magnitude in I and K band, that JWST will never reach. And this is, for example, the elliptical profile, the surface brightness profile of an elliptical galaxy, and you see here the limiting radius that you can survey with these different telescopes. So HST, JWST, ELT. And here in the bottom, you see a direct comparison of the same similar field of view with these two different distances. I'm saying that to stress, to highlight that ELT, Mikado at ELT will be the right instrument to study in detail, for example, the stellar population around some of the Cephids to constrain and to better understand the full HST data sample. Okay, so let's move on out to 200 megaparsec now. And what we say that we will try to see if Cephids can be detected and their mean magnitude estimated and their period estimated in Coma. So how to the Hubble flow. This will also have as a legacy value the increase of the sample of Cephid and supernovae 1A host galaxy. So in some sense we can improve both. We can have an independent estimate of H0 but also increase the sample where you make the supernovae 1A calibration. This also was discussed in the Maori White Book with Vincenzo and Ilaria mainly as collaborators. Okay, so we did this experiment. I anticipate that this is an experiment and also these are the first simulation, so is a work in progress. So I'm just showing you something that I try to make available for this conference. Okay, we decided to simulate a field in Coma. To make it, we have to constrain the stellar population in the field that we want to simulate, and to make prediction, to constrain our theoretical models, we used the real data, in particular on M31 taken with the NIRCam from the FAT team. So this is one of the last data release of the FAT team. In particular, we focus on the brick 22 with low surface brightness, and we get this color magnitude diagram for M31, so real data, and we also had some young population because we wanted to simulate also a field where Cephids were in there, so blue loop stars. Okay, concerning Cephids, as input to put in the image, we used a theoretical light curve, and in particular we sampled 20 epochs in a large range of mass and periods, so covering periods from 5 to 100 days. And you can see here the models that have been just picked randomly from 0 to 400 days. And this is the result. I mean, these are Cephids just with noise, but this is the field that we have simulated using the SCAO mode, 8-hour exposure time for each epoch, quite long, and a pixel scale of 4 mass to assure a nice signal to noise ratio. So it was already fine to us to look for Cephids, at least for the brightest one, and just making a quick and dirty photometry, so very, very fast. I show you the day of total star photometry. You can see the Stetson index where variable stars show up, and in particular you can see here the one with very bright and so with longer period, and the errors on the magnitude that we have. So already we have checked for variability for some of them, and we were able to find again back the inputs with the periods with some shift in the periods in this range, but also for some of the Cepheids that have a lower Stetson index and that are fainter. So this is promising. Of course, this is a very preliminary analysis, so I'm not very quantitative on this, but we will follow this study. So the point now is that very probably we will see Cepheids in Coma, but of course we will see the tip of the Cepheid, so only the very long period one. But we know that these Cepheids, and this is a work we are doing with Musella, Ilaria is leading this work, on that there is some dispersion on this ultra-long period Cepheid that is higher of the one that you see for shorter period. So these we have to understand if this is intrinsic or if this is only a problem of data reduction, etc. So,
Juliana,
yeah.
You're eating into your Q&A time now.
Okay, but I'm just finished, because these are my conclusion. And answering if ELT can help in setting the Cepheid distance scale, we can say that yes. Of course, I'm sure that he will do a good job in the 7 to 40 megaparsec range. We need to investigate what we can do to Coma. And I'll leave with this.
Thank you very much, Juliana. And sorry to have to interrupt you. So far, people are a little bit shy when it comes to asking questions. The first one that's currently in the list is the lack of blue sensitivity of the ELT cam a limiting factor for the study?
Yeah. For sure, we are, I mean, we know from HST data, but also from ground-based data, that variability is much better to be examined in optical band, of course, because of the larger amplitude. So usually what you do is to make a search in optical and then go for near infrared, because on the other hand, infrared tools like the periluminosity relation in H band or in K band are much less sensitive to metallicity, and at the same time they have very small spread around the relation, so are the most robust in some sense. So the answer is yes, because we are not used to look for variable stars in near infrared because the amplitudes are very small, but maybe it will be done. Or we can also think something else, like to use other instruments, like for example Miras, which is an extreme adaptive optics in optical, to make search and then move to near infrared, or follow up HST data, of course. I mean.
Great, thanks. The next question comes from Adam Rees, and it's: how good will the photometric stability of ELT be for measuring light curves?
This is a very good question, because adaptive optics data have not been used very much for variable stars search. However, it depends on the use that we have to do. I mean, for detecting, I think that it will be challenging. Instead, for crowding search, it will be not, because usually you use the best potential in the center of the field of the adaptive optics, and so you focus where the PSF is not so much variable, and so the stability is not very important. I mean, it is stable.
Thanks. Next question is from Anonymous. Is there an ELT GTO program on Cepheids?
Not at all. I don't think, I mean, we don't know how it will work. So far, there is not. But also there is no, it's not fixed, the GTO for ELTs, so I don't really know.
All right, thanks. And the final question, what are the respective strengths of the various 30-meter class telescopes for distance ladder measurements?
The different
respective strengths, so the differences between the telescopes and how each of them might be better or worse for distance
I
learning?
don't think there will be among the ELTs, I don't think there will be a lot of difference. I'm more expert in ELT, but I'm sure that Nefarious for TMT and the other camera for GMT will make a very similar job. So I don't think that there is a very huge difference between among the ELTs telescope.
Okay, thanks. Can you please now, okay, I can stop sharing, I guess. So Stefano, you're up. And thanks again, Giuliana, for your talk. And now is Stefano Casartano on the James Webb Space Telescope and the distance ladder. You're currently muted, Stefano.
Thank you. I'm sorry, I'm trying to share. Was that successful?
I can currently just see your video. There you go. Yes.
All right. So I'm sorry. I will just go to start on the presentation. I'm sorry. I just had to. Okay. Thank you very much for asking me to present some thoughts and some indications of what might the future might hold concerning the distance scale measurements, especially as it concerns JWST. There are other future telescopes. Juliana has spoken about ground-based telescopes, Euclid and the Roman Space Telescope will also contribute, but I'm going to focus only on JWST. And let me say just a few things about the H0 tension. We've seen this plot many times. It's adapted from each other the summary of the Kavli conference last year. Three things that I want to mention. The H0 tension is not due to a single measurement. It's very hard to think of one systematic that will make it go away or reduce it substantially. Many of the data points shown in this graph have completely independent systematics. And the one thing that I think is important to keep in mind is that chipping away at the tension by taking out 1 sigma here and 2 sigma there is not going to help. Because unless we find that some of these points are actually wrong, or the error bars are wrong by a significant amount, 2.5 sigma events in the same direction are just as unlikely as 1 5 sigma event. Now, what would JWST do? In a summary, JWST will sharpen and validate several of the local data points, and I will try and spend some time on what I think we can expect there, but also, most likely, JWST will provide something completely new that we haven't even started thinking about. Just to have an idea of the capabilities of JWST, I cannot possibly do a justice to what JWST will do in this talk, but the launch day was supposed to be 2021. I don't know why the one has disappeared there. As you can see, JWST will cover a huge wavelength range from 0.6 to 30 microns with a multitude of instruments, imaging, spectroscopy, IFU type analysis instruments, chronography. There is a lot to look for. And there are already 13 early science programs that have been approved. And the Cycle 1 proposal was supposed to be a few months ago, and it's been delayed because of the COVID-19. Okay, I also want to just, I'm not going to read all the slide, but I just want to say a few things about what I think makes a good distance scale indicator. Actually, Wendy Friedman in the panel discussion already has made a few of these points, but just to reiterate, distance scale indicators are physics-based, based on a well-understood theoretically solid physical principle, like stellar stability, stellar equilibrium equations, Kepler's law, stellar evolution theory for TRGB is very important because it means it's possible to understand what systematics might exist and to look for them and to test them in a much better way. Deterministic measurements are better. Methods that are based on an estimate for a single object are preferable to statistical ones, although statistical ones can be very powerful too. It's just a little bit harder to understand outliers and systematics. Accuracy is important as well, and in particular for methods that need to rely on supernovae. Usually the local supernovae are not very many because these methods have finite reach, and so it's important that the accuracy per system is not dominated by the accuracy of the method, but rather by the error in the scattering supernova properties. Precise local calibration is important. That's one of the strengths of the Cepheids, which have so many different methods for calibration, while other methods are now maybe newer and have fewer ways to calibrate them locally. And finally, small, well-understood, and correctable systematics are very important. Okay, all of that is smarter than apple pie, but I think it's important to keep it in mind. And when new ideas come up, people should really look at what strengths and weaknesses are for any new method. So let's now move to Cepheid specifically. At the moment, the two major errors or uncertainties in the Cepheids are the local calibration, which will hopefully be incredibly improved by Gaia with EBR3 coming later this year or early next year, but also the number of supernova hosts. We are working hard on that. 19 have been published so far. We have 19 more in hand, just finishing the reduction. So that number of hosts will double, and that means that error bar, the light blue error bar that now dominates that will shrink by a lot, will shrink by 40%. But there's still going to be a significant turn. Can JWST help? Well, we are running 2 experiments with HST in cycle 28, which might help understand what JWST can do. The first one is pushing the Cepheid limit, which so far has been around 45 megaparsecs, further out to 70 megaparsecs. This is an example of, this is NGC 5468, which is the furthest host among the Cepheids hosts have been published so far. We have a couple there just a bit further. And the simulator the panel below is simulating the observations of the same galaxy out to 70 megaparsecs. A lot more Cepheids would have to be discarded because of these reds, because of local surface brightness or confusion issues. I will get back to confusion in a moment, by the way. But you still have tens of available Cepheids. So there's been a proposal led by Dave Jones that has been approved for 110 orbits for 5 galaxies, reaching out to about 70 megaparsecs. That, if that's successful, which we expect, will not only make a measurement of galaxies of supernova hosts much further out than ever that has been done so far, but also quadruple the possible volume for supernova 1A, because you can go to 70 megaparsecs instead of 42. The caveat there is that when you go to such large distances, you're going to be limited to brighter, longer period Cepheids. So the distribution of Cepheids is going to be more limited towards the high end. Which also means, since those Cepheids are rare, that you need a Cepheid-rich host, so a bright late-type galaxy. And you'd have to worry about crowding a little bit more, although crowding is probably not a problem now. The other project is actually going to the Coma cluster. Coma cluster, there was a very ambitious program back about 10 years ago to identify Cepheids in Coma clusters. That program was interrupted because ACS died, and when ACS was revived, additional observations were made with WISI. And a number of Cepheids were found in NGC 4291, which is in the Coma, and it's actually known to be close to the core of the Coma cluster in terms of velocity. And of these, about 22 with period longer than 33 days are below what we believe are reasonable confusion and reading thresholds. So we have 17 orbits approved to do the IR observations for these Cepheids, and we expect that it will give us a supernova independent determination of H0 to a precision of about 4%. That's much worse than we have for the full H0 determination from SHOES, but this term is completely independent of supernova. And because there are two supernovae, two type 1 supernovae in Coma that have been measured, then we also can leverage those to obtain additional information. Now, if these 2 experiments are successful, that means that HST actually will be able potentially to double further the number of accessible supernova hosts to about 75, and then reduce that error bar by another factor. But JWST would help a lot, at least as far as IR observations are concerned, because JWST 100 megaparsecs is the same as HST at 40 megaparsecs, since it has 2.5 times the diameter, and so 2.5 times the resolution, and 2.5 times squared the collection area. However, there is a problem that Cepheids are a little bit difficult to find in the near infrared. The amplitude in the H band is only 0.2 magnitudes instead of the 1 magnitude that we can take advantage of in F350 LT. And so the searches that require 10 epochs will be fairly hard to make, and JWST solutions are inefficient. So it's unclear that JWST is going to be a great Cepheid finding machine. It's a great Cepheid measuring machine. So it's possible that a JWST and HST may need to be combined for optimal results. Okay, let me say a few more things about crowding, since it also came up again today. This plot shows the scatter in measured in deviations of individual Cepheids from the mean for their galaxy. I'm sorry about that. And you can see two things. First of all, there is a little bit of a, there is a very small dependence of the residual with crowding. If you look at the blue dots, which are binned values, they deviate very little from the mean value. Also notice that while the mean of type 1a supernovae is a mean Cepheid crowding of about 0.2 magnitudes, we measured that directly for each Cepheid with artificial star tests. Actually, one of our hosts, NGC 4258, is well past that. And so we have hosts at 0 crowding, the Milky Way and the LMC. We have calibrators at 0 crowding, and we have calibrators at high crowding. So just to summarize, photometry of Cepheid is definitely sensitive to local cell density. We can correct for that with artificial star tests. We find no difference between hosts that are, for each host between the Cepheids that are above or below the median crowding. After making our corrections, of course, there is difference, but the correction seems to take care of that very accurately because there is no residual, no systematic difference depending on local crowding. The 6 supernova hosts that are more crowded than 4258 and the 13 supernova hosts that are less crowded than 4258 don't show a difference in the relative contribution to H0. Also, the paper that Adam Rees presented and Juliana just mentioned shows that the amplitude suppression that we measure in the infrared is fully consistent with the crowding estimates. And that's been tested all the way up to 25 megaparsecs, which means half the supernova hosts at the moment. And there was no free parameter in that. And of course, there was also a paper by Richard Anderson and Rees in 2018 to look at actual objects that were physically associated, binaries or clusters around the Cepheids, and showed that that was negligible. So in my view, crowding has been entirely systematic. Now, JWST will still help because it will reduce the scatter. It will reduce the crowding and will improve distance accuracy. Let me just say one more word about the plot that Juliana just showed. We agree that crowding is real. There is no question that crowding is real. There is no question that the amplitude decreases as magnitude increases. That's predictable. We actually can demonstrate that with a very simple analytical formula, and which finds direct confirmation in the data. But the point is that crowding can be measured in 2 different ways, and giving the same result can be corrected for. And the scatter here, by the way, is mostly due to the fact that the amplitude measurement in the infrared is based usually on only a handful of measurements, because we don't take infrared every epoch when you take the visible. And so the signal noise in the amplitude measurement is actually low. All right, I hope that we can put that to rest for now. So in summary, HST and JWST together may be the answer for Cepheids, because HST can effectively find Cepheid to at least 70 megaparsecs or with extreme effort all the way out to Coma. JWST can easily obtain near-infrared photometry with better signal noise and crowding in that range. And we can expect to be able to reach many more supernova 1A hosts, as well as reach directly into the Hubble flood. Perhaps we should bank HST now, get some galaxies measured, find Cepheids in some galaxies at the extreme distances, and then get JWST photometry later. However, I just wanted one word there. Everything is about systematic control in this game. We're not going to reach close to 1%, 1.5% without taking good care of our systematics. So SHUS has been able to reduce and nullify many systematics by using the same instrument and photometric system throughout. We need to repeat that full calibration sequence if we were to use the JWST. And the LMC and the Milky Way may not be as easy as they've been hard with HST, they may be even harder with JWST. Okay, so now two other methods have been presented to reach into the supernova hosts, TRGB and Miras. The TRGB method has a lot of promise for JWST. Currently extends to 30 megaparsecs, but 30 megaparsecs are hard. The 10 supernova hosts published so far, with more to appear soon, have required a fairly large expenditure to reach the TRGB. JWST, communication from Meredith Durbin and Rachel Beaton, JWST can reach 30 megaparsecs in an hour or less. The accuracy is comparable to Cepheid and is applicable to early type galaxies. At the moment, the number of hosts that can be reached is smaller. JWST can do better, even with a few hours of observation of the galaxy. There is a paper I wanted to highlight here, a paper by Meredith Durbin and collaborators that shows how multiple bands can be used to identify and to optimize the identification of the TRGB, the edge of the red giant branch, by just doing various combinations. It's a very complex paper, very good. I recommend people read it, but I think time to get into it. However, I also want to point out, this is a slide from Rachel's talk, that one has to be careful about color. There are very strong color effects. The edge is very color dependent. And so when you have a systematic of that magnitude, you have to be careful about it. And probably using multi-band data will help. The problem with TRGB at the moment is that the calibration is still a little bit uncertain. There were two papers last year that showed that reddening in the LMC handling the reddening in the LMC differently made a difference of about 0.07 magnitude, 7%, which is significant when you want to measure the Hubble constant at the level of 1 or 2%. 7% in magnitude is 3.5% in distance, of course. And I don't want to get into the details, just to say that some more work is needed. Rachel presented in her talk that 4258 is more in agreement with the Friedman-Dahl calibration. So it may be that other calibrators will help, but this data are not published yet. So we'll look forward to more details on 4258. Jerry and Walter collaborators have presented a way to calibrate the TRGB from objects in our galaxy using Gaia parallaxes. And actually, we have started a project with John Soltis, a grad student at JHU, to do a fully Bayesian analysis of field stars and W clusters in DR2. The work is progressing, but it's very hard to do. We want to be very careful about systematic and statistical challenges, both of which are significant. This is an example of what you can get for a single globular cluster. We now have more than that. We have about 24 here with a combined luminosity function. Many more will have to be added, but we have to be very careful how the parallaxes, parallax errors and uncertainties and systematics are dealt with. So the work is still ongoing. It's basically just started.
Sorry, Stefano, I think your slides are frozen. Could that be?
I don't know. Is it possible? I'm going to turn off my video because I know I have a limited amount of. Okay. Have you seen the slide change?
No.
All right. So sorry about that.
Maybe just reinitiate the screen share.
Okay. Let me do that. Okay. I'm sorry about that. I cannot find my Zoom window. I'm sorry.
I will stop sharing for you.
Okay.
And then you can just re-share the.
Yeah, I apologize. Can you see it again?
I see that you've started screen sharing, but I cannot see a slide.
Okay, let me see if this helps. I'm really sorry. My computer seems to be going over some problems.
There we are. So now I have, now I see your presentation.
Okay. Let me see if I can go into Okay, I'm sorry. I don't seem to have presenter mode. I don't seem to have. Let me try again. Is this better?
Yes, thank you.
I apologize. Okay, so I was there. Okay, so one thing I wanted to mention about Miras is that JWST can be transformative. Miras are complex objects. They have, Caroline Huang gave a good talk on them, but focus mostly on oxygen-rich Miras, these black points, as opposed to these gray points, which are carbon-rich Miras, because carbon-rich Miras are much more complex. They're brighter, but they have circumstellar envelopes that can cause problems. Now, if you were to observe these Miras in the further in the infrared, like 3.6 microns, you could see that this is a paper by Kramer et al. That the period luminosity relations are much better defined for Miras, and they can be separated easily by using infrared colors. So redder bands can provide the key to bright long period Miras, can extend the reach, and JWST can reach 50 megaparsecs for the brighter Mira variables, carbon-rich variables, in 1 hour per epoch. Now they're still going to be they're still going to be hard to find because you require multiple epochs, but the potential for Miras to understand them better and to use them as better calibrators is actually great with JWST. One more thing about cosmography. We have seen a very nice talk by Kenneth Wang on the capabilities of time delay cosmography with current facilities. But what JWST can do is it can help enormously by providing very high resolution spectroscopy, stellar population measurements of the kinematics in the core of the lensing galaxy. And so there is a paper by Ilderim et al. That appeared a month ago or so, which shows that with NIRSpec IFU kinematics, you can yield a 3% uncertainty just for the single lens. And if I understand correctly, in this contour, the gray contours are without the kinematic constraints, and the pink contours are with the kinematic constraints. So there's a potentially huge improvement that can be made by obtaining kinematics for a lens like this. Okay. So in summary, JWST will bring significant improvements in local distance estimators, precision IR photometry for more distant Cepheids, which may need HST as a search engine, better characterization of Miras, and that's a whole new chapter to open, if you will, where Miras are very good today, but they can become much better tomorrow as we understand better their properties, both oxygen-rich and carbon-rich Miras. And the reach of JWST in that case is going to be very, very useful, although one has to be careful about the cost of the searches. And more distant TRGB with the opportunity to explore different filter choices, but we need attention to calibration and improved model constraints. And those are the ones that I came up with that I could talk about today, but let's expect the unexpected. A facility with the capabilities of JWST, covering a range of wavelengths that have been very modestly explored so far, is likely to bring up something completely new and brilliant in the future. And let me conclude this with a recommendation. As we talk about social justice, let's not just look outside, let's look at ourselves and our field. Recently, a colleague has shared a letter written by Lauren Chambers, who was a Yale graduate, a recipient of the Chambliss Prize from WS, and a former colleague of ours, who left astronomy and wrote an open letter saying, entitled, "It's not me, it's you." And one quote I will just briefly read is, "Just 3 years out of undergrad, I've accrued countless stories of dear black and brown friends who've been literally abandoned by their graduate advisors, black and brown friends who've been yelled at by research advisors, black and brown friends who have faced both colorism and sexism from mentors, black and brown friends who have been forced to change jobs due to lies from the bosses, black and brown friends who have been underpaid by their advisors compared to white peers." And I want to emphasize this. Some of these advisors, mentors, and bosses are vocal and well-known allies. Some of them are widely celebrated for the work they have done to improve the environment of astronomy. Some of them are women or people of color themselves. This is not a case of a few red apples, it's all the apples. Thank you.
Thank you, Stefano. That's a tough statement at the end. Very touching. Thank you. Time is very short, so I'll jump right in. Antoine Meron asks, will HST last long enough to overlap with James Webb and achieve the observations you are suggesting?
Well, James Webb is supposed to launch next year, so hopefully, yes. HST, there is no reason that HST should stop working anytime until, say, 2030. Now, we cannot promise that, but there isn't anything on the horizon. A few years ago, we were very concerned about the HST orbit that seemed to be the potential to decay. It has decayed much less than expected. We're still working on 3 gyros. We have 3, so we can work potentially up to down to 1 gyro. Something can always happen. We cannot tell, but right now things are very nice.
All right, thank you. And the last question from myself: how good will the James Webb Space Telescope long-term photometric stability be for light curve measurements?
The detectors for JWST are much better than the WC3IR detectors. They're in the same category, but they are much later generation. I don't think there is any reason to expect any long-term change in those detectors. I think I would be very optimistic.
Okay, thank you very much, Stefano.
And sorry for the problems I've encountered with technical issues.
It's all fine. I'm sorry that we have to cut Q&A a little bit short, but we can pick that up again during the panel discussion. Our next speaker is Elisabeth Krause on future probes of dark energy.
Hi, can you hear me?
Yes.
Excellent. First of all, thank you for putting together this really interesting conference. I've tremendously enjoyed listening to talks from so many different areas the last few days and certainly learned a lot. And it's great that we were all able to come together in these times where it's impossible to travel. And thank you for being so thoughtful in how all these interactions can still go on online. I've enjoyed a lot. I've been asked to talk about future probes of dark energy, weak lensing and large-scale structure specifically. All this right now and in the future is the work of very large collaborations. I would probably need the duration of my talk to list all the people that have contributed in some way or another to the thoughts and results in here. So let me just start by saying that much of what I'm discussing here is based on discussions and analyses in the Dark Energy Survey, the Vera Rubin Observatory Dark Energy Science Collaboration, and the Nancy Grace Roman Space Telescope Science Investigation Teams. And with that, I'll talk about the future. Let me start with a brief preview. This is the future of dark energy, but I'm now talking about cosmology parameters of future analyses. I believe that in many of these large-scale structure and weak lensing analyses, systematics will become truly the limiting factor as we push to better and better statistics. So our analysis parameter chart in about 2025 might look like this, that there's about 5% of parameters that we know how to model really well. And those are our cosmology parameters. And then another 75% systematics, comprising known unknowns and previously unknown unknowns. And we already know that we will have fantastic telescopes in the future. The job ahead now is to make sense of this large systematic parameter space and be ready for the updated theoretical models that people will develop and that will hopefully be ready for data analysis in a few years. To set the stage for talking about the future, let's briefly start with a very quick review of photometric dark energy surveys. For weak lensing, that starts already in 2002 with first detections, and then moved on to survey science in the early 2000s with CFH, TLS, and Cosmos, getting weak lensing results, cosmic shear, and the deep lens survey slightly later. These all followed different survey strategies in terms of survey area on the sky, shown here by the blue area, and galaxy density, which approximately represents survey depth. Right now, we are in a golden era of cosmic shear surveys with the kilodegree survey, the dark energy survey, and HIPAS and PrimeCam, following slightly different survey strategies, all operating on a similar timeline, learning from each other and from each other's analyses. And these are really the training ground to prepare us to make sense of the billions of galaxies that will arrive in our detectors in the mid-2020s. We have listed the big weak lensing, the LSS surveys of the next decade by approximate start date. Of course, there's some question marks to that, but in the next decade, we will see Euclid and the Nancy Grace Roman Space Telescope launch, following, as currently planned, very different survey strategies. Euclid going very wide with about 30 galaxies per square arc minute. The Roman Space Telescope focusing in the current baseline observing strategy on a smaller area, but much higher depth. And then the ground-based Vera Rubin Observatory with approximately a comparable area and depth to Euclid, but more photometric bands. And while these are long duration missions, keep in mind that the first year of Rubin Observatory data will be already a fantastic data set for cosmology. So the excitement will start in 2024, not 2030. Then when we have these billions of galaxies, we will want to perform weak lensing, so cosmic shear, galaxy clustering, galaxy-galaxy lensing, and galaxy cluster analyses, and probably many others. And the goal is to get the best possible cosmological constraints to really understand where the S8 tension falls with respect to the CMB, what large-scale structure can tell us about H0, and all the other parameter extensions that might become interesting. We've seen throughout the last 20 years that the best constraints come from combining different surveys, which in much of the history of cosmology meant that we could combine independent probes and multiply the likelihoods from each survey, as shown here, for example, in the combination of BEO, supernovae, and CMB. If we now want to get the best results out of, say, the Rubin Observatory only analysis, that already means that we will have to combine galaxy clustering, weak lensing, and clusters, which probe the same underlying density field and are thus physically correlated, and they are also affected by correlated systematic effects. This is both a blessing and a curse. It requires a joint analysis, but will also help us make sense of this big parameter space. But let's briefly review the present. Hendrik already covered weak lensing very nicely yesterday, highlighting the result of all the different collaborations. In terms of preparation for these future surveys, let me just briefly show a few plots again to show you how far weak lensing and weak lensing cross LSS analyses have come. Here are a few results from the KIDS collaboration, combining with galaxy clustering in terms of cross-correlation analyses with 2DF lens and gamma spectroscopic surveys, looking at cosmic shear, galaxy-galaxy lensing, and galaxy clustering. And then also joint analysis of KIDS weak lensing and the BOSS full shape power spectrum. Hendrik talked about all of these yesterday in more detail. These are very detailed analyses, and one plot can't do them justice. But to give you a small idea of what goes on in the full parameter space, let me briefly introduce the DES year 1 weak lensing cross LSS analysis, where I know the systematics best. So similar to KIDS analysis, we are here looking at the combination of galaxy clustering. In our case, a photometric sample of about 660,000 galaxies with excellent photoses, and 26 million source galaxies, for which we have measured weak lensing shapes, split in 4 tomography bins. And then we measure cosmic shear, galaxy-galaxy lensing, and angular clustering. And at the end, we want to constrain S8, and then also in combination with BBN and BEO H0, as Julian kindly highlighted yesterday. So between that data and the cosmology parameters is still a lot of systematics modeling. where in the DSU1 analysis, we ended up with just 20 parameters compared to our earlier ambitions of having far over 100. The systematic model consists of linear bias, photometric redshift uncertainties for the clustering and redensing galaxies, shear calibration uncertainties, and intrinsic alignments. That's a lot of parameters already, but this list is known to be incomplete, and they're known unaccounted for systematics that we deal with by throwing out effectively most of our signal to noise. And these are also simplistic parameterizations, which we have to validate, and that will require much more complexity going forward. For now, though, this got us to cosmology results where you can see that the analysis of cosmic shear, clustering, and galaxy-galaxy lensing in red and their combination are consistent in this projected parameter space. And this is after marginalizing over 4 lambda CDM cosmology parameters and in total 20 nuisance parameters related to astrophysics and observation systematics. Central values of this analysis differ by the Planck results on omega meta and S8 in about by more than 1 sigma in each direction, and lie on the same side of it as other weak lensing analyses, starting from CFH lens, KIDS, and HSC. So this is getting interesting, and we need more galaxies. To prepare you for my discussion of systematics, here is one of the, I think, most interesting plots people have made reanalyzing the DES Y1 data. This is a rogue analysis. Don't try this at home or don't draw physics from it, but it shows you how much the systematics mitigation really matters. Here, Anthony Lewis compared our standard DES-U1 analysis by one where he fixed all the nuisance parameters in red. So you can see the contribution of systematics to the error budget, and then also keeping all the measured correlation function data points, not throwing out a huge fraction of the signal to noise because of uncertainties in nonlinear modeling. So you can see that the assumptions about systematics modeling are essential for the constraining power. And that's something to keep in mind as we talk about forecasts for future surveys, especially if these are made by different forecasters. Because often the parameters that are not shown in the plot are almost more important than those that are to understand what's going on. And with that, let's talk about our future surveys of weak lensing and large-scale structure, Euclid, the Vera Rubin Observatory, and the Roman Space Telescope. And since for some of them, the survey strategy is not finalized yet, in particular, the Vera Rubin Observatory, or LSST, is having active debates about that. And also the Roman Space Telescope survey strategy is not fixed yet. Let's talk about how that looks like for the current generation of surveys. In the past, in the statistics limited era, a first approximation could have been that higher number of galaxies is better. Then the next step could be to look at the combination of number density of galaxies and survey area, where of course maximizing both is really good. And for much of dark energy science, we found that prioritizing area over depth yields stronger constraints. Again, that's already subject to forecast details. But if you really want to forecast how well a survey is going to perform, this becomes a very high dimensional problem. We still have our number density of galaxies and the survey area. And then the question is, how well can we control systematics? So we have to find out how well we can optimize shear calibration for a given survey strategy, the photometric redshifts, how well we can internally calibrate intrinsic alignments, galaxy bias, cluster mass observable relation, which in particular may benefit from prioritizing overlap with different wavelengths. But in short, I think this parameter space can be summarized that all of these are expensive. So the various collaborations are currently going through the detailed work, figuring out which of these matter most and what to prioritize, both in terms of the survey itself and in preliminary work. One example quickly here to show how much systematics modeling matters. Here's a very simple forecast for analysis combining galaxy clustering and weak lensing for the Roman Space Telescope and the Rubin Observatory, showing you in the inner contours in both cases an analysis without any systematic marginalization. And then in the outer contours, marginalizing over linear galaxy bias and redshift uncertainties for the lenses and sources for each tomography bin. You can see that this is an important part of the error budget, and these assumptions matter. Hence, when I wrote a forecasting paper in 2017, I made all my forecast plots without axis values, just showing relative trends. But this idea hasn't really caught on, and I understand that it's difficult to do for science requirement documents and funding agencies, but also take that as a statement about the accuracy of forecasts, or rather the importance of underlying assumptions. In the Rubin Observatory, the Dark Energy Science Collaboration went through a very detailed forecasting exercise about 2 years ago, which culminated in the science requirement document that you can find on the archive, including links to all the data products and Fisher matrices for reproducing Rubin forecasts, these are now based on much more mature survey and analysis assumptions and understanding of systematics for all the different probes. These are joint forecasts, including cross correlations, both statistical and systematical for the static probes. And then assume that strong lensing and supernovae are uncorrelated with the static probes for now. In this exercise, we considered 2 classes of systematics. Those that are self-calibrated, that is galaxy bias, which is calibrated from clustering and galaxy-galaxy lensing, intrinsic alignments, and the cluster mass observable relation. And then those that need to be externally calibrated, that is photosys, shear calibration, and photometric calibration. And you can see that the different probes have different degeneracy directions, and that combining them, shown here in black, will, as expected, yield the best results. The Euclid Consortium went through a similar and very impressive forecasting exercise that you can find on the archive from last October, where they present joint Fisher forecasts for spectroscopic clustering, shown here in purple, photometric clustering, and weak lensing, shown in orange, and a combination of all of those, including cross correlations, shown in yellow. And there you can see the relative improvement of the constraints. Here, I'm showing you a not WA model with optimistic systematic assumptions. And they have a very nice document detailing what happens in the optimistic versus pessimistic case. So if you really want to know about future probes of dark energy, I highly recommend the study report. Let me spend my remaining few minutes with a few thoughts on forecasting the performance of the Roman Space Telescope, which has officially entered phase C. And Congress has appropriately required funding for fiscal year 2020. The project is scheduled to launch in October 2025, with agency commitment to no later than 2026. While COVID has impacted the workflow, the overall schedule impact is modest so far. And the Roman Space Telescope will combine an imaging survey with broad capabilities, starting with some relatively narrow near IR filters that can be used for standard photometric survey, including photosys. And then I would like to point out here this W filter with a very broad throughput, which you can think of as a light bucket. And then it also has spectroscopic capabilities. So in our forecasts, we teamed up with one of the supernovae science investigation teams using their detailed forecasts with modeling of the high latitude survey, which includes a spectroscopic component and imaging for weak lensing and photometric clustering and galaxy clusters. The observing strategy is not yet defined. And on the right, I just want to show you an overview over time. You can see in colors how much time the different probes are allocated, with purple, for example, being microlensing, and red being the imaging survey, so that includes lensing and photometric clustering. We then set up a forecast machinery starting from a detailed exposure time calculator and redshift distributions based on the candles W1st catalog, combining cosmic shear, galaxy-galaxy lensing, galaxy clustering, cluster number counts, cluster weak lensing, spectroscopic clustering, and supernovae 1A from another science investigation team, and combine these with the non-Gaussian multiprobe covariance, marginalizing over 80 plus systematics in a full simulated likelihood analysis. And here you can see again the performance of the individual probes, clusters in blue, weak lensing, supernovae, and then the power of combining them all. However, the survey strategy is still evolving. So we also looked at how much we could gain from this light bucket, which could get to LSST 99% completeness over the full Rubin area in about 5 months. So we could use these high quality space images for galaxy shapes, photo these from LSST and combine the two. And with that, you can see a comparison of the performance of the Roman 10-year survey, the high latitude baseline survey for the Roman Space Telescope in blue, the Rubin 10-year survey in red, and combining both of those using the white light bucket for the Roman Space Telescope, which would yield about a factor 5.5 improvement through systematics control. And with that, I will skip to my conclusions. You've seen here the gains from combining multiple different probes, much of which is by breaking degeneracies in parameter space. And because these probes all have inherent different dependencies, that means that combining different surveys will allow us to calibrate observational systematics, while combining different types of measurements allows us to calibrate astrophysical systematics. And in order to really make the best out of all these fantastic data sets coming to our hard drives in the next decade, we have to start collaborating across all these different collaborations now to set up joint analyses. And with that, then we can really maximize the constraining power by identifying and understanding systematic effects and then combining them all. Thank you.
Thank you very much, Elisabeth. Jump right into the questions. First one is from myself. Given Tamara Davis's and Hendrik Hildebrand's talks, what is your take on photoz's and their impact on survey results where spectroscopic follow-up is not realistic?
This is certainly one of the biggest systematic concerns right now. And we have been having very detailed discussions for weak lensing with the KIDS collaboration. I think Hendrik actually gave a very nice summary. We will still have some back and forth and hopefully learn for LSST. But we should also keep in mind that half sigma shifts are to be expected as we learn how to do stage 4 weak lensing measurements. So I think right now it's a healthy process and the jury is still out.
Okay. The follow-up question comes from Hendrik. Is the optimal dark energy survey also optimal for constraining S8, or are there competing trade-offs?
That will, I think, to a large extent depend on our theory priors, whether we want to marginalize over curvature, how complicated our dark energy model should be. Basically, the question is, do we really need a very broad redshift baseline to constrain all these effects? Or are we really after one amplitude measurement where the redshift dependence is pretty clear?
Thank you. Next is an anonymous question. Given the first year DES results, low S8, sigma 8 values, tension with Planck, what are your explanations or expectations?
At the moment, it is a 2 to 3 sigma curiosity, give or take. We still are learning also about reglancing photosis and other effects.
It's an argument.
Excuse me?
Is that what we put here? Argument?
Yeah.
I'm sorry, I couldn't understand.
Somebody was speaking in between. I muted the mic. Sorry.
So it is interesting. I don't think we really have the statistical constraining power yet to make strong claims. This should all get much more interesting later this summer. And we need a few more billion galaxies. I think we've carefully checked each other's analyses, have learned from it, but have not identified any multi-sigma shifts.
I just love astronomy. We need a few more billion galaxies. So what do you, next question from Anonymous, what did you think of the new SDSS 6DF peculiar velocity results Collas showed in context of lensing results?
I have not thought about that enough yet to fully comment. Apologies.
Thanks. And a final quick question. What would be an optimal SPEC-Z survey to complement the various upcoming wide field imaging surveys you mentioned?
Again, I think it depends on whether we think that we will get most gains from a full shape power spectrum analysis, in which case we really want a high sampling density to push to intermediate K modes, or whether we still think in a year from now that photoses are our main worry.
Perfect. Thanks very much again, Elisabeth. And now we hand over to Raphael Flauger, who will be telling us about the future of the CMB.
Yeah, so I think you can see the slides, hopefully.
Yes, and we can hear you fine.
Okay, yeah, so thanks very much for the invitation. And more importantly, thanks for organizing the meeting and giving us the opportunity to exchange ideas in these unusual times. And so I'll try to give an overview of the future of the CMB with a focus on what we can learn from the CMB about the current H0 tension. We had a lot of closely related talks already. A nice talk by Sylvia about the Planck measurements, nice talks by Julien and Vivien about the theory. And so I felt I don't really have to give much of an introduction, and just thought I would start by showing you directly the measurements from Planck, the temperature measurements along with the angular power spectrum and the measurement of the angular power spectrum of E-mode polarization. I'm skipping TE just because it didn't fit on the slides. There's also the lensing measurements, but altogether the measurements established that the early universe is remarkably simple and really tightly constrain any departures from lambda CDM. And so looking at this data, you might ask if there's anything more the CMB can contribute. And in this talk, I'll try to convince you that the answer is yes. And I'll try to explain where the CMB community is going and what you can hope to learn about the discussion of H0. Of course, one of the reasons it's not the end of the story is why we're all here. I mean, there are indications that lambda CDM is cracking. They come both in the form of the sigma 8 tension that has been mentioned. So there's a discrepancy between the value of sigma 8 that's predicted by the Planck cosmology in the context of lambda CDM and the value of sigma 8 that's been measured by various low redshift probes, lensing, but also TSC cross X-ray, various low redshift measurements give lower values of sigma 8 than what is predicted by Planck. And then at higher statistical significance, there's the tension between the value of H0 that is predicted by Planck in the context of lambda CDM and the value that is measured by the local local measurements here. And so the point of this plot, I just wanted to highlight that often it's phrased as a tension between Planck and shoes. And I think that's too simple-minded in the sense that even if you combine the previous sets of experiments, WMAP and the small scale experiments, you also end up with low H0. So there's really something going on between the predictions of H0 by CMB measurements in the context of lambda CDM and the local measurements. Of course, the story is either more complicated or richer depending on your taste, because we have a fair amount of additional information at low redshifts, which we heard about during the week. So there was a nice talk by Rachel about the Carnegie Chicago Hubble program. We had a nice talk by Kenneth about the holy cow strong lensing measurements, and just because it got too cluttered, I left off the mega masers and the Miras, but there's a lot of information in at low redshift, and so overall it's interesting and worth understanding what's going on. We've heard a lot about the low redshift measurements, and so it makes sense to have a quick discussion of what we can hope to learn from the CMB. And before I talk about the future of the CMB, I just wanted to make one additional quick point about these kind of comparisons, and that is that sometimes there's a discussion whether this could just be systematics in the Planck small-scale temperature data, and I think that's also difficult to see how that could come about, because it's true that if you remove the small-scale temperature data, the Planck measurement shifts up to in agreement with WMAP, as one would expect, but you don't have to necessarily add the temperature data back in, the small-scale temperature data back in to get low H0. You can also alternatively just add the low L polarization, and that also pushes you down. So there really seems to be something in the CMB data that, at least in the context of lambda CDM, favors small lower values of H0, and so there seems to be something that is there to be understood. So before I talk about the future, let me briefly show you what the current set of experiments look like. So there's the bicep KEK experiment that everyone knows, then there's SPT, there's a balloon-based experiment SPIDER, Polar Bear, Simon's Array, Advanced ACT, which should have a publication soon, is my understanding, although I was also told that a year ago, so hopefully now it's true. Then there's also CLASS. And if you look at them, you see that they come in all kinds of shapes and sizes. So there's a 30-meter aperture for 30 centimeter aperture for bicep, 10-meter mirror for SPT, 3 meters for Polar Bear. Here I'm just showing you the cryostat, but it's a 6-meter mirror, primary mirror for Advanced ACT. And I thought it's maybe worth explaining a little bit why they actually look the way they do. And to do that, I have a figure here that's a little bit busy, but it kind of highlights, I think, where the community is going and why the experiments look the way they look like. Here, what you see is, on the one hand, the blue measurements by Planck, and that they really very well agree with the temperature spectrum, the theory spectrum. You also see that that set of measurements is essentially done because you're really reaching angular scales where there's diminishing returns, because there's extragalactic foregrounds, and the silk damping implies that the primary CMB drops exponentially, so you can't really push it much more. You can push it a little bit further out, but not significantly. Then if you look at polarization data, you see that Planck also mapped out a fair chunk, although this now depends a little bit on how it's plotted. And you see that on small scales, there is unexplored territory. And in the plot, the way I showed it in the plot here, it's in the log scale, it's a little bit misleading, because really, even though this looks small, you have to keep in mind that at a given L, there's 2L plus 1 degrees of freedom. So there's actually more information left in the CMB that hasn't been measured than information that has been measured. And so there will be significant improvements as time goes on. Here, there's also the gray bands indicate the error bars for upcoming surveys. And you see that the measurements here will be really precise out all the way to very small scales. And then on large scales, Planck did provide us with a measurement, but it's very difficult, challenging, because the satellite wasn't really designed particularly for this part of the measurement. And so I think this is the part that has to be measured again. And then in addition, on large angular scales, there's also the chance of observing primordial gravitational waves. So this is one of the excitements. And the other excitement is here, the small scale polarization. And together they really contain invaluable information about astro and particle physics that remains to be extracted. And from this plot, it's also kind of clear maybe that there may be different telescopes involved. So if you look at the large scale polarization, here, as I said, it's a sensitive probe of any gravitational waves that might be present at recombination. And according to general relativity, they're really a pristine relic of the primordial universe. You couldn't really modify them. And in the foreseeable future, the imprint on the polarization of the CMB is really our only way to detect them. They're statistically independent just because we think that the density perturbations were generated by the inflaton, let's say, and these are genuinely the quantum fluctuations in the space-time matrix. So they really provide a completely new window on the early universe. And because they peak on large angular scales, you can get away with relatively small telescopes, and you want to get away with that because that gives you better control of the systematics. So those telescopes roughly have 1.5 meter optics tube with, let's say, 0.5 meter aperture. Then on the small scale polarization, here we know that it constrains the number of relativistic species, the sum of neutrino masses. I'm not going into detail exactly which part constrains what, but overall the small scale polarization contains information about these, about the properties of dark matter, whether there's any couplings between the dark matter, the baryons within the dark matter, some information about dark energy properties, although the CMB really isn't necessarily the best way to look for dark energy, as we all know. Then it also constrains the statistical properties of primordial density perturbations, both whether there's a running, non-Gaussianity, isocurvature perturbations are much better constrained. And then this is also the part where you can learn about the Hubble parameter, again, through the angular scale of the sound horizon, so in an indirect way. And then it will constrain, as I'll explain a little bit more, the proposed solution to the tension. And these are much bigger telescopes. So this is a 6 meter mirror shown here. So this is a much bigger object. And so to give you an idea of the sensitivity as a function of scale, I just wanted to show you the angular power spectra in here E modes. It's slightly different. I dropped the L times L plus 1 that's usually there. That makes the noise look a little bit nicer. Anyway, so here is the E mode polarization, the lensing B modes, and the potential gravitational wave B modes that one could observe. And then I'm showing you noise curves, characteristic noise curves for the small aperture telescopes. And you see that they're very low on large scales and then blow up because of the small size. And then the large aperture telescopes are significantly worse on large angular scales where you would want to look for B modes, but they do much, much better, of course, on small scales and really give us pristine measurements of the small scale polarization. So the two really kind of separate. The one complication is that in order to do the gravitational wave measurement, you see that this is in principle limited by the lensing B modes, and so you have to remove the lensing B modes. This is referred to as delensing, and for that you need small scale polarization information. So the search for gravitational waves always comes in pairs like this. There's a large aperture telescope and one or several small aperture telescopes. And then as far as what the sky coverage will look like for these experiments, there are the gravitational wave search. You're really trying to go as deep as possible because you're looking for a very faint signal. And so you're looking for a small patch, either here's a typical scan strategy from the pole or a scan strategy from Chile with a small and large aperture telescopes. And then the other part of the survey, looking for light relics, neutrinos, and that's also the survey that's relevant if you're interested in the Hubble parameter, is a survey that really tries to capture as much as possible of the sky in as homogeneous as possible way. And this is the survey, one of the scan strategies for the survey in Chile, which would give you 70% of the sky. So hopefully that gives you an idea why the experiments look the way they do and what they look for. And now let me just show you the ones that are coming up. So on the one hand, there's what will be the South Pole Observatory, which is BICEP, Keck, BICEP array joining forces with SPT. So this is exactly the combination I just mentioned, looking for primordial gravitational waves and observing a small patch of the sky as deep as possible until about 2024 or so currently, as far as I know. Then there is the same type of effort going on in Chile, where Advanced Ag, Polar Bear, Simon's Array are all joining forces to become Simon's Observatory, and we'll also have two, here in this case, two surveys, essentially one focused on primordial gravitational waves, one wide area survey with a large aperture telescope. And then you see this trend of groups coming together. This trend will continue, and there will be one big ground-based experiment of the entire, at least US CMB community, hopefully also with international participation, from taking data hopefully between 2028 and 2035. And this will involve both the site at the South Pole and the site in Chile. There's also hopes to have a satellite mission. The Lightbird mission is led by JAXA and was selected by JAXA last year, is planned to launch in 2028. And it has resolution comparable to the small aperture telescope. So it's not really comparable to Planck in that sense. It has lower resolution, but of course will cover the full sky, and is really focused on the search for primordial gravitational waves. But I'll show you briefly the H0 forecasts as well. Then we also did a probe mission study that is called PICO. This had, or has, if it happens, this is still much more up in the air, much less clear, has a much higher angular resolution, much more sensitive than the other instruments, and would observe the full sky and be able to do all the different science goals with the same instrument, which obviously has advantages. So briefly, the usual caveat that I already mentioned, the CMB doesn't really directly constrain H0, or in rather limited ways. And the way it works is that we know the photon energy density from the CMB temperature. So obviously there's the well-known Miras measurement. Just in response to the discussion yesterday, I wanted to mention that there's actually another measurement. So even if you don't trust Miras, there was the Cobra measurement by Gosh, Halpern, and Wishno, which also measured the CMB spectrum and measured a temperature of 2.736 plus minus 17 millikelvin, which I translated here into the energy density of photons. So even if you throw out Miras, you're not completely stuck. And once you know that, you can, the anisotropies provide tight constraints on this set of parameters, but you also see that the local measurements don't really measure any of these parameters directly. So what you do is you pick a model and derive the other parameters, like the Hubble parameters, sigma 8 and so on. For example, for lambda CDM, as everyone knows, you take the angular scale, which is then a function of h, omega cold dark matter, h squared, omega bh squared, and you solve it for h to give the constraints that are quoted. And let me just show you the forecasts. The forecasts for in the context of lambda CDM. The forecast for Simon's Observatory, you would expect about 0.4. For S4, it's about 0.2 all in kilometers per second per megaparsec. Then even the deep survey for CMB-S4, so the survey for the search for gravitational waves, returns about 0.9 uncertainty on H0. And that also means that you can chop up the sky and really look at what's going on as a function of direction, if there's anything that suggests there's anything funny going on. The constraints from Lightbird are around 0.3, and PICO is significantly more sensitive than the other instruments, would return something like 0.09. Obviously, that by itself isn't necessarily the right question. You might ask what happens if you open up some of the other parameter directions, and if you have some favorite directions. I can generate forecasts for you here. I'm just providing you some numbers, what happens when you allow n effective to float. For Simon's Observatory, you get about 0.6, S4 about 0.4. And then here you see Lightbird degrades significantly more because it doesn't have small scale information, whereas the D patch for S4 still has that. PICO gives you these kind of constraints. So the precision on H0 in the sense of the prediction based on some cosmological model will be very high going forward, but it's maybe not the only thing you want to ask about. you may want to ask, how does it constrain the kind of departures that we've been discussing? And here you have to distinguish between the early and late modifications, as was done many times. The CMB has very limited information about the late time modifications, but the large-scale power spectrum measurements, both BAO and full-shape power spectrum measurements, really tightly constrain H0 and are consistent with lambda CDM as inferred from Planck to very low redshift. And so it looks very difficult to have a meaningful late time modification. Doesn't mean it's impossible, but it's certainly not easy. You can look at the nice talks we had yesterday by Nathalie, Julien, and Vivian if you want to know more about this. For the early universe, because the angular scale is given by this ratio, this is set at late times. The other option is to change the sound horizon. I didn't include much because this was described very nicely here. But the very nature of the sound horizon, which is just how far sound can travel in a given time, tells you that modifying the very early universe doesn't help you in any way. If you modify the early universe when the universe is only a second old, the sound can't travel much more, can't travel more than a light second. And so really to change the sound horizon, you have to do it around the time of recombination, or at a time when the sound horizon is of order 10 or 100 megaparsecs. Otherwise, there's just no measurable change. And so that means that you're necessarily changing the physics at a redshift of 10 to the 3, 10 to the 4. And the main point is that this is exactly when the modes that are probed by the CMB enter the horizon. And so as a consequence, the measurement of the damping tail in small scale polarization will provide really tight constraints on any of these departures. And so this is what I'm showing in this plot, again, the busy plot from the beginning, where I'm just plotting roughly the redshift where the mode that we see enters the horizon. And you see that it covers exactly the redshift range that you would want to probe to test these departures. And you see, this is a forecast of error bars, so it will be exquisitely small. So it's not like now where you can just hide in the uncertainties. It will be very tightly constrained and really either exclude these modifications or find evidence for them. And so I leave you with the conclusions that you can read. They're just a summary of the talk, essentially. Thanks for your attention, and thanks again for organizing the workshop. I really enjoyed it.
Thank you very much, Raphael, for this exciting talk and outlooks on the CMB. I have one question so far in the list by Anonymous. And the question is, do you think it's time to push for a CMB spectral distortions mission?
I'm always in favor of the spectral distortion missions. I'm not sure that this is necessarily too closely tied to the question of H0, but overall, I think it's been a long time, and there are interesting things one can do with the spectral distortions. I mean, the mu distortion has interesting information about the primordial power spectrum, has interesting information about you could imagine decaying or annihilating particles. So it really constrains a lot of things. You can also look for recombination lines from hydrogen, which would give you completely independent and completely primordial independent measurement of the baryon abundance. So some of these things are very exciting. I don't know if there was a concrete question as to how that helps with Hubble. I have to admit I haven't thought about it. I'm generally very supportive of spectral distortions or measurements of the CMB spectrum. I haven't thought too much about it in the context of the Hubble tension, I have to say.
All right, thank you. Another question by Anonymous. What is your view on A-lens in the CMB analysis?
Yeah, so A-lens, I think, is an interesting question. Obviously, it's not really a very physical parameter, so it's the amount of, so there's A-lens, I guess I don't know if everyone knows what A-lens is, so let me just say, A-lens is a parameter that's introduced into the analysis that's supposed to change exactly how much lensing there is, if you wish. On the one hand, you can measure the lensing through the smearing of the 2-point function, the peaks and troughs in the 2-point function. I probably don't have time to explain the physics, but if anyone wants to know, I'm happy to talk about it more later. But so you can measure it there. You can also measure it in the 4-point function. And there is an indication from the smearing of the 2-point function that a lens wants to be higher at a 2 or 3 sigma level. I'm not convinced that that's, many people will say that that's statistical. I'm not sure. I think this could indicate that there's some systematic issues in the data, or it could be that we're missing something else. It doesn't really even 100% look like a lens to me. So I think whatever is going on is probably not really just this peak smearing, but is something that we're not quite doing correctly. But even if you marginalize over that parameter, it doesn't significantly allow you to shift H0. So it allows, there are various reasons why you would think that the H0 value from the CMB could be a bit higher, could be 68, could be 69 maybe, but not higher than that. And that's consistent also with allowing a lens to vary. So I'm not sure what a lens is. It's not just a lens. I mean, there's something going on probably, but it doesn't per se help with Hubble.
Okay, one final question, also by Anonymous. Are there any quote unquote funnies in the CMB that concern you?
Any what, sorry?
Funnies.
Funnies.
So I'm
just something that looks funny in the data.
That's going on weird or something like that, I presume, yes.
I mean, the low L data looks pretty peculiar. There's a lot of things one can look at in the low L data and get amused by. So those are kind of funny. There's the cold spot. There's this asymmetry between hemispheres. There is a systematic difference in power between even and odd multiples at low L. So there's a lot going on at low L. But there you're also limited by cosmic variance, so it's unclear what to exactly make of it.
Okay, thank you very much again, Rafael. Now I would like to ask all the panelists of today, so that's Juliana, Stefano, Elizabeth, as well as Licia, Tom Shanks, Sorab, and Jose Luis, to all turn on their videos. And I will hand over to Licia for guiding the panel.
Yes.
Licia, I think your video is frozen. Perhaps the better idea would be to turn off your video if the
do you see the
isn't very stable. Licia, can you say something, please? Unfortunately, I do not hear anything.
Can you hear me now?
Yes, I can hear you now.
Oh, okay. Excellent. So, well, welcome to this discussion session for day 5 of this very interesting conference. Before I start, I saw a few times a plot being called Verde plot, but actually it's a plot that is the summary of a conference that was held this summer, and the author is me, but it's also Adam Rees and Tommaso Treu. And the plot actually was made by Vivienne Bonven, and it's available in his GitHub page. So if you look it up, it's a GitHub called H0 tension, and you can customize the plot from there. So anyway, so we had a very good array of speakers today, and today was mostly about the future, but by in the last session, we'll also have to do a little bit of wrapping up. And we have a panel here. It's me, it's Tom Shank, it's Saurabh Jha, and Jose Luis Bernal. and we had some discussion about how to do the ordering. So I decided on an order, and we'll see if you understand the logic a posteriori. So let me start by saying that we should ask, where is the problem? And I think it's clear now that the problem is not in any specific data set or in any specific analysis. This has been repeated by a few speakers, but I think it's obvious from the summary of all the presentation. So there seems to be two values for the measurement, some cluster around the 68 camp, some cluster around the 74 camp. There is one measurement in the middle, which is in the 70, which is the tip of the red giant branch, but there's not much to the left and not much to the right, which is quite interesting. And the other thing that it's sort of clear to me by listening to all the talks is that somehow we keep going round and round in circle, because we always think within a Lambda CDM-like model, and we try to do simple extension from the Lambda CDM-like model and see if we get somewhere. As Lloyd Knox was saying, in the quest of model X, right? We try to move away from a Lambda CDM model, and I would like to say that maybe one should try to also do a slightly different approach, which is also to look for maybe model-independent quantities rather than look for model-specific fix. I'm not saying we shouldn't do the other one, but maybe we should do both and see if the model-independent approach gives you some guardrails that will guide you in looking for the famous model X. Now, this is hard, and H0 is a wonderful example because it's one quantity that you can measure locally in a way that is completely independent on the cosmological model. And then you can measure at the other end of the universe from the CMB, but in a way that really depends on your assumption about early time physics and the model. And you can measure in the middle, as we've seen, but then you need to also make some assumption about cosmology. So maybe one should at least drop a part of the assumption and see if something emerges. And, you know, one thing could be doing early versus late, another things could be doing local versus global, and Tom will have a slide about that. And this is particularly timing given the future prospect that we've seen today, because if you want to go beyond parameter fitting, typically the error bar grow a lot, but with more data, you're probably able to do both, keep the systematic under control, and also make this kind of effort worthwhile rather than meaningful, rather than just blowing up the error bar. And also the other suggestion for all the speakers is that the solution that with today's data may be indistinguishable may actually be leave signature in the forthcoming data. And, you know, I wonder if you know or can guess which one they may be. So it's not all just an H0 problem. We've seen it's also an RD problem. It's also an omega matter problem. And so I took this unpublished figure from Jose Luis Bernal, who is actually going to talk more about the robustness of the BAO interpretation. But in this plot, the horizontal green line is what you get from supernovas plus BAO. The orange line is what you get from the CMB, and the vertical line is what you get from the local measurement of H0. So it's not just an H0 problem, it could also be seen as an omega matter problem. And the other thing I want to point out, this is a slide from a conference that went on in October, and one of the sessions was also about the H0 tension, and the title of the slide was "How old is the universe anyway?" And one of our panelists next will say more about that. And I want to mention that also the age of the universe can be constrained or estimated from objects that can be observed relatively locally, but of course have information about the whole history of the universe. And it's a very long story. These are the globular cluster, and that can give for certain a strong lower limit on the age of the universe, because as we know, the universe can't be younger than an object it contains. Again, if you want to connect age and H, you also need omega matter and a model. And so we all go back to this model independent and relying on the model depending on what you want to combine the different observations. So I'll just move on and ask Jose in my order to go from more model dependent to less model dependent, or more model independent. I put Jose's first.
I would like to very briefly chime in here and just mention that participants in the audience, you're welcome to also add further questions to the discussion panel Slido page, and
Please.
I will try to bring those into the panel as much as possible.
Okay. Okay. Yeah. Thank you, Licia, for introducing that. I wanted to emphasize one thing that Silvia Galli mentioned on Monday. Licia, I think that you are still sharing a screen. So, okay. Yeah, something that Silvia Galli mentioned on Monday is that in the quest to find that model X, we shouldn't cherry pick our data, and we should use all the data available. And in that sense, BAO is impressively powerful for constraining tensions on the models to solve the tension in the Hubble constant, because they connect, as Natalie Palanque mentioned yesterday, they connect the early and the low redshift universe. And the standard BAO analysis uses constraints on these compressed parameters, alpha parallel and alpha perpendicular, that basically gives you constraints on the shape of the Hubble constant, sorry, of the Hubble parameter with redshift, but also gives you a constraint on the product of the sun horizon and the Hubble constant. The concern that many theorists have with these measurements is that the standard analysis uses a template fitting. That is, they assume and compute a template for the fiducial cosmology, and then marginalizing over the broadband of this power spectrum, just distort this template in order to fit the data. And some people were concerned about this not being robust and valid in order to do model independent constraints, because they would depend on the fiducial cosmology. So recently, in a paper with Tristan Smith, Kimberly Boddy, and Mark Kamienkowski, we checked this and found that for those models that modify the growth of a structure prior to recombination, which it seems to be the preferred way to solve the tension, as Loinos mentioned the first day of the conference, the BAO are extremely robust and there is no bias. Here I'm showing some examples for both low C and C mass and forecast for DESI, in which we check this for different models using always a template for the fiducial cosmology, and only if you go for the most extreme cases in which the universe will have to be more than 3 sigma away from the data of Planck, of the power spectrum of Planck, we find below 1 sigma biases in these parameters only in one of the cases. So I just wanted to emphasize that we also provide the way to for anyone to check their model against the robustness of the BAO, but encourage people to use the BAO because they do not depend, at least at the precision that we have now with BOS and that we will have with DESI, they do not depend on the fiducial cosmology that you use to that is used to constrain the data. So we should use all the power that we have in the data right now.
Thank you. So I move on to Saurabh.
Yeah, thanks, Licia. So this is actually, following on what Licia was saying. First, I wanted to thank the organizers for this really great conference. And the conference, of course, has been focused on H0, the Hubble constant. And that's obviously of interest to us. But I thought maybe we'd take this opportunity in this panel for the last day to think about a little broader context. And so a more general audience. And so if you search for the Hubble constant, you get about 100 times fewer search results from Google than you do if you search for the age of the universe. And if you search the age of the universe, so there's 600 million hits there for the age of the universe. And if you search Google for the age of the universe, it very authoritatively tells you that the age of the universe is 13.8 billion years. Okay? And so for most people, that if they wanted to know this answer, that's what they would do, and that's what they would see. Some people, budding scientists might dig a little bit further and go to a more reliable source than Google. And of course, much more reliable than Google is Wikipedia. And so if you go to Wikipedia, then so it's circled there, you can see that the age of the universe is around 13.8 billion years. And what do they mean by around 13.8 billion years? It's 13.787 plus or minus 0.020 billion years. That's the age of the universe. 20 million year uncertainty. Now, of course, it's nice that there's uncertainty listed. That comes from the Planck results, of course, and it comes from assuming a lambda CDM. Okay, and as obviously the whole conference here has been that there is some tension in those results, and there's tension with other measurements. So I think it behooves us to be a bit more realistic about what is the uncertainty in the age of the universe. And I see Adam had asked this same question in the Slido. So on the left is, of course, the age of the universe is model dependent. It is, directly related to H0 just being inverse H0, but as Alicia mentioned, it needs a model. So even assuming flat lambda CDM, then you have to specify the matter density. So this plot shows some CMB measurements with the physical matter density on the y-axis and H0 on the x-axis, including the shoes measurement. And so the question here, of course, the tension between the purple small Planck contours and say the local universe measurements, obviously that's what we're trying to address at this conference. And so it's going to depend on what the resolution of that tension is, what age of the universe we should really be quoting. And so if for example, the matter density is still relatively high, 0.3 for omega matter, then you might get something like the age of the universe being less than even say 13 gig years. And so the 12 point something gig years. If omega matter though is low and it follows along the contours, then maybe the age is still 13 point something billion years. So my only point here is to say that we should be a little bit more careful and clear in describing that there is some uncertainty. And so not only uncertainty from the measurements in the age of the universe, and of course, as Licia mentioned, you can actually use direct measurements of old things to constrain cosmology. So there's uncertainty from the measurements, that's the tension that we're talking about, but there's also uncertainty from the model, right? This, again, even these contours that you see are from a flat lambda CDM model, but we should be a bit open, obviously, to new physics and the idea that those models may not be the final story. And so I think we should do a better job of explaining to our introduction to astronomy students, to the public, to Google, to Wikipedia, that there are significant uncertainties with this number. We don't know the age of the universe to 20 million year accuracy. And in this time when, as scientists, communicating uncertainty to the general public is very important. We see that in the pandemic, we see that in climate change, that scientists, I think, should be careful about communicating uncertainty. And this is one area where I think we have not been as careful. We should say, sure, maybe our best guess is 13.8 billion years, but maybe it's 13 billion years. And I think we should make that clear, because when the public hears that we've revised the age of the universe by a billion years is a long time to normal people. And so, that hurts our credibility if we've said that it's very precise and then we change it. So that's all I really wanted to say. One last thing, and this week on Twitter has been highlighting Black in Astro. And I wanted to say one thing about type 1a supernova. There's a tweet there by Ken Shen. You can follow the link if you'd like. But the first person to actually positively hypothesize and show some evidence that type 1a supernova light curves are powered by radioactive nickel-56 was Titus Pankey Jr., an African-American, in his PhD thesis at Howard University in 1962. And that citation has gotten lost in many, many references. So it's something we'd certainly like to bring back and highlight and amplify, especially now. So thanks.
Thank you.
Thank you. I would just like to say that we would like to keep a few minutes also for an open discussion. Yeah. So sure. Please.
Tom?
So it's Tom Shanks here. What I'd just like to say to begin with is it's been a wonderful conference, wonderful talks, and it's quite clear to me there are some tremendous people, some tremendous teams, and tremendous leaders working in this field to measure H0, particularly by the distance scale. But what I would remind ourselves is that this is H0, this is the distance scale, and we've had great leaders in the past. We've had Hubble, we've had Sandage, we've had de Vaucouleurs, and to some extent, H0 in the end, the actual value defeated them all. So, and what usually caught them out, or the problem was they always used to get 5–10% error on their value of H0, but usually they were out by 50% or 100%. And so it was always the systematics that got them. And of course, there's been wonderful talks today on crowding in terms of calibrating the supernova scale with Cepheids. And there's many systematics we could talk about. The one I'm going to talk about, which I think has been undercooked in terms of thinking about these things, is the one about peculiar velocity. So like Tamara Davies and Matthew Collis and Dragan Hutera talked a little bit about earlier in the week. What is the error on the redshift axis? So what you see top with this plot, the top two diagrams are where we got to 2014 Whitburn and Shanks paper, where we took about, in this area, 3,000 square degrees around the South Galactic Pole. There were 3 other areas, 9,000 square degrees in total. And we took the 100,000 galaxies in this area and made a histogram of them in terms of number redshift, then divided them by a homogeneous model. So what you see here is essentially the overdensity. And what you see out to 150 megaparsecs over most of the southern sky is an underdensity of 40–50%, which we called from previous times a local hole, a local underdensity, a local void. And we saw that, this is the one I'm showing, of course, is the most dramatic, but in the other 2 areas of 3,000 square degrees each in the north and in the other part of the southern hemisphere, we saw a similar, so 40% underdensity here, 20% underdensity in those other 2. On the right, top right panel, you see that same data in the southern fields, 3,000 square degrees as the red points. And Hans Bohringer and his team, using X-ray clusters, have plotted the blue points, and you see the blue points following the red points quite nicely. And Bohringer et al. In 2015 suggested that they had confirmed the local hole with a completely independent view of the universe through X-ray clusters. And so in 2019, they also did the same in the Northern Hemisphere, but I haven't got time to show those. So we produced this result. We mentioned it recently, and we got criticized a little bit because we were only covering 9,000 out of 40,000 square degrees. And if you try to make the case there's a global underdensity locally that we are not at the center of, but is around us, then it's a fair point that we should look to see if we can convince people that it's over the whole sky, over the whole local volume. And actually, just going back very simply, we'd use the 60F Galaxy Redshift Survey and SDSS Redshift surveys to K of 12.5 to do those 2 upper graphs. But if you cut back to K of 11.5 with 2 mass magnitudes and use the 2 mass redshift survey that the great John Hukra pioneered over the last tens of years, that goes right down almost to the galactic plane. So these the first graph on the bottom left I'm showing is the whole sky now down at least to mod B greater than 15 degrees. So 15 degrees off the galactic plane. And it's showing as the dots, the histogram of data, the NZ histogram, and as the dashed line, the homogeneous model. We divide one by the other as we did in the top 2 graphs. And on the right, bottom right, we see the final result, which is the whole sky, essentially 30,000 square degrees out of 40,000 total, all that's available except in the galactic plane. And you see a 25% underdensity around us over the whole way, more in the south than in the north, but all over the sky. What effect does that have on the Hubble constant? Well, it's not so huge. It's something like 3% if in terms of the effect of that extra outflow you get from this underdensity region on the galaxy redshifts. But 3%, when you're looking for a 9% tension, and you maybe have, and I mean, Stefano Casatano in his talk today mentioned 1 ± 3% for Cepheid crowding. Well, you don't need to have 2.5 sigma. You could have about 1 or less sigma, and you've got a 2% effect still to be corrected for, possibly there. That's 3% plus 2%, 5%. Then there's what Lindegren talked about earlier, which was the Cepheid 0 point. And I noted that he said that it was essentially the Cepheid 0 point confirming the Gaia astrometry, the parallax offset, rather than the other way around. It's sometimes claimed that Gaia has confirmed the Cepheid period luminosity 0 point. And Lindegren put it very fairly, I thought, in that he's suggesting that there's still some way to go on that result. And that could easily be a 5% error, although the other people will say it should be less because there are other methods to calibrate the PL relation. So there are caveats on what I've said. Unfortunately, I haven't got time to go into them. But anyway, that's what I wanted to say in terms of my comments on what's happening in terms of H0 tension. Thank you.
Thank you. So I would like to open the floor to the questions for the speakers or the panel. But let me unshare the screen so that we can look at the questions.
Oh, I'm happy to read questions.
Yes, because, yeah, thank you. So which question has more? Please go ahead.
There were 2 questions, basically a question and an answer right away. With the CMB, we have known physics. With SN1A, we have no 3D physical model. So why should we take seriously the Shoes-driven tension as a driver for new physics, was the question. And there was an immediate answer, which is that Rees showed that even without supernovae 1A, the Hubble tension still is a 4.9 sigma, because strong lensing masers surface brightness fluctuations, and the Tully-Fisher do not use supernovae 1A. Would you care to comment on that?
Could I add a little bit to that? Yeah, so I would say first off, the supernovae do have some physical basis, right? We know that they're the detonation of about 1 solar mass of degenerate carbon-oxygen material. Now, exactly how that happens and whether that has anything to do with the Chandrasekhar mass of a white dwarf, those are still open questions, but there is some physical basis. But I think more to the point, the way we use type 1a supernovae is empirical. We don't use supernova models to do the measurement. And the H0 measurement with supernovae is really a difference in samples of supernovae at redshift 0.005 and redshift 0.05. So something like supernovae 70 million light years away compared to supernovae 700 million light years away. And you need to have a 9% shift on average of those samples to get to resolve completely the H0 tension. So, and by the way, we can measure an individual supernova to about 9% precision. So, you know, once you have a sample, you need to get that average. So I think that's a hard thing to do. We try and make those samples as similar as possible. There are some ideas, you know, maybe something with the host galaxies could make those samples different. But it's not really a lot of cosmic time, even though we don't necessarily understand the supernovae, it's not a lot of cosmic time to change the supernovae. It's very different than the high redshift supernovae, where there is a lot that you could do. You can change the populations. And moreover, there's a point which says that the span of the Hubble flow objects themselves, right? So between, say, redshifts 0.02 to 0.15 is a larger time span than the difference between when the calibrators are and the median Hubble flow object. So if there are systematics related to evolution of supernovae, we would see that in the Hubble flow sample itself. We would see the residuals were not flat. Even large voids in the universe, we would see that in the Hubble flow sample. And we don't really see that, maybe down to the level of below 1% in systematics, maybe something with the host things. Mikhail Rukko had said in his talk that maybe 3%, but still well below the 9% tension.
Could I just say, just to even things up on my presentation, there are possible issues with, can you hear me?
Yes.
Yes.
There are possible issues with Planck as well. And of course, we've talked about the small scale. When you take that away, the disagreement with WMAP is less and with Hughes is less. And what I'm not an expert, but I did look at WMAP, and to be fair, they were okay in this point. But the beam correction at small scales in Planck, I'm not an expert on it, but I presume they've done a wonderfully thorough job like the WMAP people ultimately did. But that's where I'd start looking if there was any issue between WMAP, Planck, and Hughes. I would start looking at the beam correction because that's the most dramatic effect that you can usually find in CMB data.
But it's not CMB. You can throw away the CMB. We can, maybe Raphael want to say something, but.
No, I just wanted to briefly say that there's really absolutely no tension between WMAP and Planck. If you look at the map level comparisons, the maps just agree. So I think there's really no discrepancy between WMAP and Planck. Planck goes out to smaller scales, so you can then ask whether there's an issue on small scales. I don't think the beams, the CMB bands can possibly be off by that much. If we're discussing beams in other bands like 857 gigahertz, that's a separate question, but the CMB band beams, it seems unlikely to me that that's really a source of this. And as Licia says, there are really the measurements from BAO, the full shape measurements recently that I also showed. So even forgetting completely about the CMB, the tension is still there.
But just to make the point slightly more general, isn't the point that you're not just dealing with one observation, the distance scale, which is systematics. There are still possible systematics on the Planck side or on the WMAP or on even the BAO side. And so that's why it takes a brave person to say there's a tension and not just to say we might average these two. I was always against that when it was 50 versus 100 and Rowan Robinson, let's take 75. But that actually did turn out to be closer than some of the other participants, including myself.
I'm not on Planck, so I shouldn't defend the Planck team. Maybe someone like Julia wants to speak up, or I don't know. But I'm not saying that there aren't possibly systematics within Planck. I think there may well be, but they're at a much smaller level. If you look at the uncertainties and the systematics are comparable to that, you need like a 10, 15 sigma shift in Planck. That's, I think, out of the question.
Okay.
Yeah, also regarding the tension between the high and low well regimes in Planck, there was a paper some years ago in which Planck collaboration performed a lot of simulations comparing these two, the constraints coming from these two different regimes. And it turned out that that what it seemed the tension between these two regimes in the actual measurements was well within the expectations from the simulations. And this basically that the correlations between the parameters is different in these two different regimes.
So can I just try to make my point more positive? I think everybody is to be congratulated on getting the two estimates as close as they are. And I hope this work continues and let's see what happens. And I encourage that to happen.
So I think Adam used to say it's like threading a needle from the other side of the universe. because you determine from the CMB H0 with percent or below precision, and then you measure it locally and you are threading the needle. Well, within few percent you are threading the needle. But, we are 7% off.
Well, maybe that's a good point to bridge in a question that is on Slido by Levon Bogosian to Tom Shanks. By how much would a local hole change the value of the Hughes H0?
3% is roughly the number. It's probably between 2.5. The caveat is, of course, it leaves you with another problem. Why the heck is there such a big hole when it's not, as Dragan said the other day, it's too big for lambda CDM. But so it gives the theorists another chance to look for extensions, at least that are different from trying to get H0 extensions. But I'm a simple observer. counting galaxies in redshift survey is a relatively easy task. The other caveat on that is the normalization of the model, which is the crucial bit that where we differ from, say, Hudson, Laveau, people who have done this sort of thing before. Their dynamical models are much more sophisticated than ours. I would say their number count modeling of the NZ is much more crude than ours. And I would say their models don't fit. They start to miss the number counts as you go past 12.5 magnitudes to 13, 13.5. But that's where the caveats are. So too big a local hole for LCDM, and then the normalization is an issue. But if you ignore those, I think you've got the right normalization. 3% is what you get in the, out of 9% in terms of you're looking for in terms of the tension.
Maybe we can bridge in Wendy Friedman's comment. If Gaia were to shift by only 2%, the current Cepheid calibration, H0 of 73 for supernovae, Tully-Fisher, SPF would all shift in H0 to 70 or 76, and these are not independent. Can anybody comment on that?
Now that is true. I think Adam Rees would say there is the mega mesa and the eclipsing binary 0 points to the Cepheid PL relation as well as the parallax. But as I said in a question earlier in the week, George's staff view, I know, still thinks there's a 3.5 sigma discrepancy between the mega mesa distance to 4258 and the Cepheid distances. And so
if I can jump in, this is Adam. So but Tom actually paraphrased me very well. At this point, there's really 7 different calibrators for Cepheids. 2 of them involve Gaia, but there's also HST parallaxes that are not done from Gaia. They're done from HST fine guidance sensor, and another from HST spatial scanning. So, you know, this idea that you could just do one thing has been really problematic on trying to get rid of the tension on the late side.
So do you still agree with staff view that there's a 3.5 sigma between eclipsing binary, parallax, and mega mesa in 4258, or has that been cleared up?
No, I never. I mean, George may have said that at some point, but I showed in my slide, I showed the 5 different calibrators that we published, and they're all within 2 sigma, which seems like a reasonable thing. And, you know, I just wanted to mention one thing. Maybe Tom is right that we live in a giant void. That would be tremendously exciting. One thing I would say is, you know, just in terms of mechanics, right? I don't think you can take the Shoes analysis and tag on the void because you don't see it in the supernova Hubble diagram. So you, at best, you would have to include it as a parameter and marginalize over it.
I agree with that. We've looked for it in the peculiar velocity from this type 1As, and we get the same result as you lot, as Shoes do. We don't see the peculiar velocity you would expect even at the 3% level. But in our own data where we've used galaxy luminosity functions as a standard candle rather than supernovae, they're not as accurate, but there's many more of them. We do see a result that looks more like and that's in one of our later papers on the local hole, that we see the outflow there. But we agree with you that in the type 1As, we don't see the peculiar velocity signature that 3% would imply.
Just jump in also, this is Wendy Friedman. I think, you know, we've looked at George's staff use analysis too, and I think there's still something to that we need to understand. And I think we're going to make a lot of progress on these issues in the next year or 2, but we're not done, and we should keep that in mind.
Okay, thanks a lot. Then maybe another comment or question from Slido by Anonymous. What are preferred dark energy constraints at the moment on WO or WA?
I think that here, one of my preferred ways to do this is try to be as model independent and not to rely on lambda CDM or this parameterization of the equation of state, and just try to fit the expansion history of the universe at low redshift with the data we have that is powerful and can be analyzed in a model independent way, which is basically supernovae and BAO. And it has been shown by several independent analyses that this data is very, very strong to constrain to redshift, I think below or around 0.8 right now, that even in the most free parameterization of the Hubble expansion, that it has to be as lambda CDM below a couple percent. Or so I think that we can do this in a very powerful and agnostic way, and BAO and supernovae are very powerful to do that.
So I don't know if the future surveys have anything to do on this kind of analysis that doesn't really rely on W parameterization. No.
Perhaps one last question from Slido then, which is related to, I think, what Jose was just saying just now. What are the model independent or insensitive quantities that can be derived from the CMB?
Who wants to answer? Nobody?
Well, everything's model dependent. I mean, but it depends at what level you're talking.
So usually in the CMB, we have a mix of late time information and early time information. So you can, for example, do some effort in disentangling the information that come from late time, typical ISW, or location of the peak, from the early time information, which is just the content of the universe, the sound speed, and things like that. So you always need a model, but you could deviate from the model without necessarily doing simple deviation from the lambda CDM. And I think here is where future data will actually really help.
Yeah, in that sense, I think that other possibility would be try to do an analogous template fitting analysis of the CMB as is done for the BAO in the galaxy distribution. However, the problem is that the precision of the measurements of the CMB is astonishing, and I don't know whether doing that would be very sensitive to the choice that you do to compute your template. That has to be seen.
Okay.
Okay, so I think we are a little bit over the time that was initially imposed. So before I pass it on to the organizers again, I would like to first thank again all the speakers of today's session and the panelists, of course, but all the speakers and the panelists of the previous day, but in special thanks, I think, to the organizers, because it's hard enough to organize a conference per se. It's mission impossible to actually turn it into a virtual one, given all the boundary condition, and still manage for the conference to be a resounding success. So thanks a lot. On to you.
Thank you so much, Licia.
Thanks.
Somebody screaming? Okay, thanks a lot. So this concludes today's discussion panel. And for these final announcements, I would ask everyone to please turn on their videos so we can see each other again. First off, just as Licia just said now, a big thank you to all of today's speakers and panelists. And also, I would like to very warmly thank all of the speakers and all of the panelists from all the other sessions for making this a memorable event and for being such active participants by asking questions and participating in the discussions and presenting these wonderful results. And this was a suggestion by Tom Shanks, which I really liked. So I'm going to give you all a round of canned applause. Here we go.
It almost worked, Richard.
Oh no.
Didn't quite hear it as loud as that.
Okay, I'm sorry. Well, I applaud it. So thanks to all of you, and thank you also very, very much to the Scientific Organizing Committee. And this time I'm going to list you in reverse alphabetical order, because as a person with a last name starting with A, I'm usually in the front, and I know that that's unfair. So thank you, Licia Verde, Dan Skolnick, Michael Rigaud, Hiranio Pyrus, Chachung Gao, Wolfgang Gieren, Claudia de Ram, Frédéric Corbin, Matthew Collis, Annalisa Calamida, and Chuck Bennett. Locally at ESO headquarters here in Garching in Germany, it's a pleasure to thank Stella Maria Casiotis-Klingner for her efficient and friendly assistance with just countless administrative issues and providing guidance for conference planning. There was an exceptional amount of work on her this time because we first planned an in-person meeting and then converted it to the online world. Also, of course, to Nelma Alas da Cunha Diaz da Silva for helping us navigate through some last-minute issues. We'd like to thank ESO safety and logistics personnel for helping us set up this conference here in the Fornex room at our H0 2020 Control Center, and for making this possible in a safe environment during a health pandemic. Mario Schilu from ESO IT helped us set up the control room, so thanks very much. And then I would also like to very warmly thank all of the colleagues who showed very strong enthusiasm over these last few months for making this e-conference a reality and for contributing ideas for how to make this a success. And I unfortunately was not able to write down all the names of the people who contributed ideas. So from the top of my head, I would cite Jason Spiramilio, Michael Hilke, Giacomo Beccari, Remco van der Berg, Mariana Haida, Dominika Bilitzalek, Anna Miotello, Carlo Manara, Sarah Mancino, and of course also our ESO Director for Science, Rob Iveson, as well as our ESO Director General, Xavier Barcons. To all the others I forgot to mention, I'm sorry I forgot to include your name, but your help was nonetheless appreciated. My very special thanks go out to my two Scientific Organizing Committee co-chairs, Sherry Suyu and Antoine Meran. Thanks a lot for making this an exciting e-conference, and first off for even making this an in-person meeting, and then for being super enthusiastic about making this a reality in the virtual world, even when we didn't have a blueprint to build on. So this was really great, and I would not have been able to do this without you two, and could not imagine a better team to have done it with. Last but not least, a warm thank you to all the participants, especially those of you who braced the very early morning or very late night sessions. Thank you very much for being here. This should have probably occurred to me earlier, but I guess as astronomers, we're a bit predestined to do conferencing very late at night or early in the morning, especially the observers among us. So I think it's safe to say that we reached many more people with this e-conference as an in-person meeting would have. And we hope that you could all draw motivation and inspiration from this meeting going forward. And we will look forward to seeing all the progress that's ahead in the nearby future. So this is Richard Anderson signing off and closing the H0 2020 conference at ESO. Goodbye, have a nice weekend, and stay safe.